So the title of my talk is At Microsecond Scale Within a Data Center. And of course, I have a picture of an iceberg, right? So don't overanalyze what that means. There is no moral statement about it. There is no Titanic off-frame running into the iceberg. It's just there to illustrate something a little bit more simple than that, which is we live in a digital era. And the digital era that we live in is completely dominated by the cell phone that we all have in our pockets. Our cell phones are only interesting because they're the visible part of this digital world. And behind this, there is an invisible part. There's one which is the internet. It was mentioned by Marie. But for many of the services that we use today, the invisible part of that iceberg is actually implemented in data centers. And these data centers are massive buildings with lots of computers in them. The biggest data centers of the world alone, according to this article, consume approximately 1% of the world's electricity. And that is, by the way, expected to double or triple during the current decade. And so these data centers are both, you can view them as a system, a machine, as well, of course, as a building that has lots of machines in it. And it's duality that makes a set of open and interesting problems in the field of data center systems, which is my area of research, and data center infrastructure in general. And if you look at the literature, a number of papers have been published around this. There are 3 papers that were published by Google engineers and scientists that describe some of those big challenges in data center systems. The first one is this surprising result that it's particularly hard to get an energy proportional use out of what's going in the data center. You have a device, a machine that consumes, let's say, 40 megawatts of power. You would somehow expect that the amount of power consumed is proportional to the amount of useful work that is actually happening and produced by the data center. And that relationship actually does not hold. And that is what we call the energy proportionality challenge. There's another challenge, which is we want our interactions with the cloud or the web or our applications in general on our phones to be fast. Now, to get speed, you need to distribute the data on thousands and tens of thousands of these machines inside the data center, and you need to aggregate the results back. And aggregating the results back so that there is good latency and good tail-latency is another challenge, and that is the tail at scale problem. And then the third one is the fact that in a data center, the amount of useful work is actually dominated by the amount of communication infrastructure and the cost of moving data around, packaging data around so they could actually be efficiently used. We okay? Okay. So these 3 papers have motivated the bulk of my research at EPFL, except the last part, which is around what became in Switzerland Swiss COVID. But all the other tracks of my work at EPFL are dominated by this notion of how to get efficiency out of data centers. And I'll only talk about 6 results in the theme of microsecond scale tail latency remote procedure calls. So let me just first define the terms, because we may not all be familiar with them. So microsecond scale latencies matter, and if you want to get some motivation, there's a lot of papers that have this title, or microsecond scale, and the title of course, from my lab, but also from many other labs in prestigious institutions. But you can legitimately ask yourself, what's really so special about microseconds? Well, every field of science has their own natural units for when it comes to time. We have a lot of physicists in the room. You're lucky because you can go from the femtoseconds or the attoseconds all the way to the light years. This is for you. So physicists have this massive range of time scale that is relevant to them. When you're a computer scientist doing computer systems, there actually are only 2 time scales that matter. The first one is nanoseconds if you build hardware, because our circuits operate at gigahertz speeds, and so everything that happens in hardware is order of nanoseconds. And the other one is milliseconds, because everything that we do that we schedule from an operating system in terms of interrupts occurs at microsecond rates, millisecond rates, so basically 1,000 times a second. Now, between nanoseconds and milliseconds, we have 6 orders of magnitude, and in between is the microsecond scale era of computing, and this is where a lot of action happens. And that is because it is the natural timescale unit of interactions between computers within the same building. Right? Data centers or buildings are the same. This is a diagram that illustrates very, very precisely how long it takes on a relatively old device. You connect two computers next to each other on a 40 gig NIC, and it takes precisely 4,300 and change nanoseconds, which is 4 microseconds. Now, these two computers in this example are directly connected to each other. Of course, if you want to connect them to a network, they have to go through switches. Well, the good news is switches only take less than a microsecond in latency. And then to get to the switches, you have to go through cables, and these cables are fiber optics cables. And the good news is that a packet can travel quite a distance in a microsecond in a fiber optic cable. In fact, when I use this slide in the lecture, I always ask my students, well, how much distance can a packet travel in a microsecond? And invariably, if the group is small enough and there's enough testosterone in the room, one will shoot from the hip and will say 3 kilometers. Right? Or somebody will say 3 meters, right? Your mileage may vary, right? And then invariably, somebody a little bit more sophisticated thinks through the math and will say 300 meters. And of course, the physicists in the room know that the correct answer is 200 meters because it is the speed of light through glass, not through vacuum, that matters. But all of this is irrelevant. What's relevant is what's written here on this slide, is if you put 100,000 computers in the same building, which is roughly the size of a modern mega data center, these 100,000 computers are only a few microseconds away from each other in any particular pair and combination. So that's the microsecond scale part. The second part of the talk and the title is remote procedure calls. Right? Of course, nobody really cares about remote procedure calls. I always have a hard time introducing remote procedure calls, but luckily I called my friend Elon, and Elon basically helped define it for everybody else. Actually, to much debate, right? There's 4,000 people who believe they were sufficiently worth their time to comment on what he meant by remote procedure calls. Now, actually, Elon doesn't talk, he talks about web remote procedure calls. So this is the interaction between your phone and a cloud data center. I actually don't care about that type of remote procedure calls. I care about only remote procedure calls that occur within a data center. So the client machine is inside the data center, and the server is also inside the data center. So these are interactions between two machines, again, that are connected to each other at a microsecond scale. So the latency is orders of microseconds. Now, if you actually look at any combination of large number of clients, large number of servers, load balancers, application protocols, you can basically measure characteristics of remote procedure calls in terms of latency, throughput, and you basically get graphs that look like this. Right? The first one measures the latency, typically the tail latency, very often the 99th percentile latency as a function of the throughput. And the red line is what is called the service level objective. That is actually what Elon wants, right? Elon wants to make sure that your service level objective is at a certain line so that the customers are happy. The second graph is basically shows the distribution of latencies for a given load. And the third graph describes the amount of energy that is consumed for a given load that meets the service level objective. And we'll go back to what these things mean. And of course, if as an engineer, what you try to do is you try to analyze these systems and build better systems that move the curves to the left or move the curves to the right. And that is precisely what we've been doing in the lab. And the first project that I want to talk about is a project that we start with students from EPFL and students from Stanford called IX. It was published in 2014. And IX was the first protected data plane operating system. It uses hardware virtualization to protect the operating system data plane from applications. And it runs on dedicated resources. It has direct access to I/O resources. Today, it's also what is commonly known as kernel bypass. And so what we basically do is we're comparing an application, and you can think about your application being a database system or a memcache key value store. And we don't modify the applications. What we do is we modify the operating system that is running below the application. And you can actually see that the choice of operating system matters. What you have in blue is the latency versus throughput for Linux, which is the universal canonical operating system running in data centers. And in black, you have the performance that we got with our prototype. Right? And what you basically see is there's a massive increase in the transaction that you can actually achieve before violating the service level objective, and about a reduction in the factor of 2 in the tail latency at low loads. And there's a reasonable explanation as to how we get to such dramatic and impressive results, is that Linux is actually a mess, right? This is actually a simplified picture of the networking subsystem stack of the Linux operating systems. I will spare you the details. Sufficient is to say that this comes with a very, very complex interface that was largely designed in the 1980s and a very complicated and convoluted code paths. And of course, our prototype is simple, and when you get to describe your own prototype, you could get to actually simplify it as much as you want, and this is basically the simplified view of how our systems work. There's, of course, details, but think about it as a loop that iterates between kernel mode and user mode with predictable transitions. From an architecture perspective, this actually has a number of benefits because it improves your locality, removes unpredictability, and therefore reduces your tail latency, and of course increases your throughput. So we published this, got great success. One of the authors who was a student at Stanford got a job to be a professor at MIT. Everything was good. But then we decided at EPFL to actually keep looking at this particular problem. And we realized that there were a number of sweeping simplification, which is the classic trick that we do as academics, right? We sweep a whole bunch of things under the rug. And one of the things that we swept under the rug was how much energy does this thing actually consume? And so I'm reproducing the same graph as before, right? On the left y-axis, you have latency as a function of throughput in black. And in blue, we added another axis, the right y-axis, which is the amount of energy that is actually drawn by these systems as they operate and as you vary the load. And if you look at the solid blue line, which is the energy used by X, it is nearly flat. And that is exactly the opposite of what you want, because what you want is something to be energy proportional, and we have something that is nearly flat. Of course, we didn't talk about it in the first paper, so it wasn't a big issue. But suffice to say that performance has an energy cost. Now, performance, the energy is actually a function of the configuration of the system. And I want to highlight here one thing is this was running with one very specific configuration of a computer, configured to run at 2.4 gigahertz, configured to use 8 cores. These were relatively old systems at the time. But you can actually change the configuration of these computers. And as you change the configuration of the computers, you may actually vary the amount of throughput that you can get before violating the SLA, before you hit and cross the red line. But you may consume more or less energy. And what we did is we sort of brute forced the problem. There's only 224 combinations of configurations at a system level for a computer. And so we computed these 224 configurations, and you effectively plot different curves. And some curves go more to the right because they can get more throughput, but they require more power at lower loads, and other curves use less power, but they don't go as far to the right. And if you take the lower bound and the minimal value across all these curves, you get what economists call the Pareto frontier, right? Which is a concept of resource allocation from the 19th century, about how to allocate the most efficiently possible your resources. So we computed the Pareto frontier of these operating systems, and here we have some good news, right? We have an operating system, our prototype operating system called X, and if we just consider hypothetically the Pareto frontier of energy consumption of X and find the right configurations, it's always or nearly always better than Linux. And so, of course, the challenge is how do you come up with a system that can basically walk and approximate the Pareto frontier, which means always at any point in time use the optimal resource allocation decision so that we can minimize energy consumption while at the same time meeting our service levels objectives. And that is basically what we did in building the control plane for X. There's a bunch of challenges. The third one is something that I'm most impressed with. I was most impressed with when we actually designed it, but it's a little technical. I'm going to focus on the second one, which is very simply, if you have a control loop, you need to make decisions as to when and how you remove resources. And that is precisely what we did. And this example shows how we evaluate it. We run a system through a loop over 4 minutes, 240 seconds. The load varies in big steps, right? So it's a very challenging workload from a system perspective. And what we basically see as expected is we need to add resources on the way up, and we can remove resources on the way down. What's interesting is that if you start from the smallest possible configuration, the first thing to do, and then that's not completely intuitive, is you should add cores but still run at the lowest clock rate, which is 1.2 gigahertz. And only once you run out of cores do you actually increase the clock rate. At least this is true for applications that have good scaling, such as Memcache. And on the way down, of course, you do the reverse. And the graph below shows, sort of proves whether we violate the service level objectives or not. And the short answer is we do fine, except when we don't. The violations are relatively short. But what's interesting about this evaluation is it actually saves a tremendous amount of energy. If you only use the maximum configuration at all times for this workload over those 4 minutes, on average, you would consume 91 watts. With our control plane, our control loop, we only consume 48 watts. And furthermore, we can actually claim that 48 watts is actually pretty good because it's only 7 watts more than the Pareto frontier. And we know by definition that there's no way we can get lower than the Pareto frontier. Of course, this is not all. There's a bunch of other sweeping simplifications in these systems. And one of them is that X was designed as a shared nothing data plane for both network and application. And so there's basically a design that leads to very highest level of performance, practically no contention, but transient imbalance and head-of-line blocking. And for those of you who study queuing theory, right, it is a decentralized queuing system, which of course is suboptimal in comparison with a centralized queuing system. So the goal, of course, is how do you build a system that maintains the performance levels but actually operates or approximates the behavior of a single queue system. And we're able to do that through a set of very efficient techniques called work stealing using low-level interprocessor interrupts. And ZGOS, which is the paper we published in 2017, was actually the first microsecond-scale work-conserving scheduler. And if you apply this new work-conserving scheduler on top of the X data plane, and your application is an in-memory database running, and this is for you, Anastasia, the most important benchmark in the database world, which is TPCC, well, you see there's basically a 1.6x speed up over Linux, but more importantly, with respect to our prior publication, there's a nearly 4 times reduction in tail latency at various loads. So we learned a lot of things in the context of these projects, to embrace sweeping simplifications, to be cautious of the sweeping simplifications. This has had a lot of impact. At the time, it was quite esoteric. Today, in the Google data centers, on millions of machines, there are kernel bypass, networking data planes that are running and powering Google's data centers. And we also realized that TCP is actually far from being the ideal transport if the only thing you care about are remote procedure calls, which is actually true for data center interaction. And there's a bunch of reasons for this. And so we ended up coming up with a new protocol, and that new protocol is called R2P2. And R2P2, and I'll skip all the details, you can try to decipher the diagram, right? R2P2 has one really, really important property if the only thing you care about is RPCs, is that the destination IP address of the request does not need to be the same as the source IP address of the reply. Now, if this statement resonates with you, I encourage you to read the full paper. If not, we'll skip to one of the really interesting applications of this protocol, which is it allows us to revisit, and this is for Rashid and Anne-Marie and all the other luminaries in consensus algorithms. It allows us to revisit how we think of classic computer science problems simply by changing and substituting the protocol. So the non-Byzantine permission consensus problem is one of the most classic problems in computer science. It was sort of defined and addressed in the 1980s. They're well-known protocols, Paxos and Raft. They're well-known implementations and systems. And actually, this is not just theoretical. These things actually matter a great deal. A lot of systems depend on the correct implementations of this consensus algorithm. And the consensus algorithm itself has perfectly fine and understood behavior. The implementation of consensus on top of protocols such as TCP to model the interaction between the node creates a whole kinds of issues, and in particular creates an artificial trade-off between availability and scalability. So the more nodes you add to a consensus group, the less performance you get. And of course, that is perhaps obvious or not obvious, depending on which way you look at it, but this is something that we actually wanted to address. And this illustrates why we effectively create this artificial bottleneck between clients, proxies running on leaders, and followers. And that allowed us to sort of revisit this problem and come up with a new way of thinking about consensus. It's not a new consensus protocol. It is the integration of the consensus algorithm into the network transport layer, and that was published at Eurosys. To summarize what we did in my lab over the last 10 years, is build a research methodology on how to build and think about computer systems. Designing and building systems so that we can reason about how they act and their actual performance, And there's a methodology involving some precise way of looking at the problem from a design perspective, not using advanced mathematics, but very basic modeling techniques, identifying the applicable systems principles, and then working on a precise implementation so that we can actually prove that we're actually delivering performance that is close to the expected behavior and bounds of the system. And the way we prove this relationship between the expected behavior and the measured behavior, among others, is by using a methodology that we pioneered in the lab that has now been picked up in academia, which is to use synthetic benchmarks, micro benchmarks that use synthetic execution times with known distribution so that we can, from these known distributions, derive known lower bounds for the behavior of our systems. I want to spend maybe a few minutes on my current line of work, somewhat different, still in the context of data center system, but what I believe to be probably the most important problem that we're facing now for our digital space, which is trust, and specifically trust in the use of public clouds. And public clouds basically are built on a technology called virtualization, which I know quite well. And the question is, how do we add confidentiality and integrity properties onto virtualized stack? So I actually know virtualization sufficiently well that I even decided to write a book. This was published in 2017. You should always write one book in your career, and then you realize how hard it is to write a book. That book actually, one of the important chapters, it's actually chapter 2 of that book, talks about the important theorem from 1974 of Popek and Goldberg, which actually has the merit of very precisely specifying what is necessary and sufficient in terms of computer architectural foundations in order to have a virtualizable architecture. And this is basically something that has been grounding the way we think about virtualization in the VMware days, and then subsequently with the addition of hardware support for virtualization. So what is the problem? We have a lack of trust in public clouds. Public clouds are built on virtualization, but virtualization in its normal implementation leads to a sort of a trust hierarchy where every layer depends and has to trust the lower layer, and that leads to a massive trusted compute base, or TCB for short. And this is compounded by the fact that we know that cloud providers may be honest but curious, which is a very precisely defined term in computer security. And in fact, it's not that we think they are honest but curious. We know that they're legally bound in some cases to be honest but curious. And of course, this poses a problem for the confidentiality of the data that's processed in the cloud. But the good news is at least virtualization is understood because of this 1974 theorem. And at the same time, we have this new emerging technology, which was actually originally designed out for desktops so that we could watch movies but not copy them, called digital rights management. And that technology, which is a little bit of a mess, effectively is now transported on servers and is the basis for what we today call confidential cloud computing. And so the research project in my lab has both a theoretical aspect and a practical aspect. We're trying to identify what are the necessary and sufficient architectural support to add in hardware in order to have both trust, which is integrity and confidentiality, as well as virtualization to be compatible with the current models. And from a practical perspective, we're trying to build a prototype that actually runs an existing hardware that has those capabilities. I want to have a few thank yous. First of all, the work I described is not my work. It is really the work of the graduate students, right? We cannot overemphasize the importance of the work of graduate students, in particular in computer systems, where somebody has to actually build the systems, write the software, get it to work, fix the bugs, and it's not me, it's actually the graduate students. So I want to first acknowledge the alumni from my lab. I'm extremely proud of my 3 alumni who are now assistant professors in prestigious places on all 3 continents, so I've got all 3 covered, right? I'm equally proud of my alumni who now have important positions that use the skills they've developed in companies. These companies all happen to be GAFAMs, right, these days. Some are in the US, of course. Some are in the United Kingdom, and 2 actually work in Switzerland. I also want to thank my current PhD students. They're somewhere in the back. I'm equally confident that they will do as great work as the previous generation. The lab would not be complete without a very, very deep and special thanks to Maggie. She's been holding the lab together, especially in the phases where I was not there too much in the office because I was in my second office or my third office, or out of the office. So thank you, Maggie, for everything. I want to thank my faculty collaborators from EPFL I had the pleasure of working with, doing research with, or teaching with. Jean-Cédric, that's for you. The SDSC has been quite an adventure. It was mentioned by Rüdiger. It runs because of Olivier Verscher, who is the executive director since the beginning. I also want to acknowledge my partner in crime, Andreas Krause from ETH Zurich, for being good sport, always working with me to resolve problems rather than creating ones. And last but not least, we're getting there. Right? I want to thank, there's a few external lecturers that I invited from some of my classes way back. Also, friends who've served on juries when I needed an external examiner. Thank you for your support. Thank everybody from the Deanship office in IC. The ICIT team who's over there, and particularly the ones who build the IC cluster. The team that is currently building the research computing platform for all of EPFL. The staff from EDIC for making my life easy as the head of EDIC. And then the entire teams from the DSI and from Human Resources that I had the chance to manage as Vice President. Maybe switching to French, j'aimerais également remercier, puisque j'ai parlé de mon rôle en tant que vice-président, mes collègues de la direction de l'époque. Vous voyez comme on était sérieux, on avait tous des cravates. La direction actuelle, qui a confiance en elle, pas besoin de cravate. Les 3 doyens et les 2 présidents pour leur confiance. 3 plus 2 égale 4, évidemment. Et puis, évidemment, j'aimerais remercier mon épouse Marie-Christine, mes enfants, pour tout, en particulier pour m'avoir soutenu, en partie dans les périodes où je travaillais beaucoup et je voyageais beaucoup. Et puis, au-delà de ma famille immédiate, ma famille plus large, mes parents sont dans la salle. C'est un plaisir de pouvoir faire sa leçon inaugurale avec ses parents, comme je suis sûr qu'Anne-Marie a le même plaisir. Et puis, les cousins qui sont également là. Merci beaucoup.